Hello, in this video we're going to look at the exponential family of distribution, specifically the Weibull distribution. Now, in order for the Weibull distribution to fit into the exponential family, we have to hold constant the shape parameter, and I call it K in my distribution down here. But this is a follow-up video to the mean and the variance of the exponential family, where we found the mean and the variance generically of this exponential family, and now we're going back and showing that it works for specific distribution, the same sort of theory and approach. We also showed that if you could manipulate the density or probability mass function into one of these forms, it's considered being a part of the exponential family. The second one's called the canonical form. So let's look at the Weibull, and it's written, the density is written like this, where lambda and k are positive and x is greater or equal to 0. Now here we have to assume that k is known. Then now we start manipulating this into one of these forms. So we take this part here, we take the log and then exponentiate it so it doesn't change it. You know, this is equal to this. This just carries down. Now we start thinking about, you know, a function of the x's, function of the parameters, sufficient statistics, so like some sort of multiplication, and then a function of the parameters by itself. And so here we have lambda and x, and it's kind of a multiplication, so it's probably going to be part of that. The lambda here raised to the k can be thought of as lambda to the k if you combine those. And then you have x by itself. Maybe it's a product, I don't know. I think ultimately we're going to try to take that out. Now, of course, in retrospect, I would have just taken the x to the k minus 1 out and then exponentiated everything else. But this is kind of the way I started, so this is the approach that I'm using. Not the most efficient, but the way that I did it, and I thought it might be helpful. So now here, since we could isolate this x by itself, that's just a function of the data, function of the x. And then everything else, since this is e to an exponent, we can just add the exponents, and that's what we do here. So the log of k is here. Now we're dividing by lambda to the k minus 1, so that's where the minus comes out. And to the k, not k minus 1, because we're combining those. So the exponent can be brought out front. And now here we have the minus, and we have x to the k, and then if we bring up the lambda, it's to the minus 1, but it's raised to the k power. So we're here. And then we're actually finished. So if we put this first and this second, then we're in the exponential form. So this is a function of our data. This is a function of our parameters times a function of our, data. And then we have what's called the log partition, which is just a function of the lambda. And it has to be minus this because that's the form that we want up here. And this is it. So it does fit into the exponential family. And this raised to the k, that's one of the reasons why we have to assume it's known, so it's not a parameter. So the canonical form, what you do is you rewrite the eta of lambda, you just call it eta. So that's our new, we reparameterize it into just eta. Now the log partition, this part here, has to be a function of eta. Now, so that means when we plug in what we know about eta, which is minus lambda to the minus k, when we plug it in here, then we get this back. And so this is the appropriate function for the log partition, or a of eta. So this is in canonical form. And the beauty of that is now that we know the log partition, we can start taking derivatives of this, and we get the moments of our sufficient statistic. Now here the sufficient statistic is x to the k. So that's what we're finding the mean and the variance of. Now, I did some videos earlier where the sufficient statistic was just x. But here we're taking this the mean of the sufficient statistic, which in our case is x to the k when it's a Weibull with k known. And that mean, by the theory of exponential family, is just the derivative of the log partition with respect to eta. Now we put in the value of the log partition. Now we start taking derivatives. So this is minus 1 over minus eta times the derivative of this, which is minus 1. So those, we just get this. And this is constant with respect to eta, so it's 0. Now we plug in what we know about eta, which is minus lambda to the minus k, solve it, and we get lambda to the k. So that's the mean of x to the k, is lambda to the k. Now to find the variance of our sufficient statistics, so it's the variance of xk, that's the second derivative of our log partition with respect to eta. So now we found the derivative once, so let's just cheat and put it in and then take the derivative of that, and we get eta to the minus 2. Or it could be thought of as 1 over eta squared. Now we put in what we know about eta, simplify it, and we get eta to the 2k. And so that's the variance of our sufficient statistic, x to the k. Well, that's all I have for today. Hope you enjoyed it. I sure did. Like the video and subscribe so you don't miss the next one. Thanks. Bye.